Hello and welcome to Mechanical Systems Design. In this video, we're going to launch Project 4, and I'm just going to quickly go through the project description here. You should also separately read it carefully to get all the details. This project brings together everything that we've learned this quarter and introduces a few new technical topics. So here's what you're going to do. You're going to design, fabricate, and test a robot in a team and upload some videos and a report on your project. And we've assigned you teams. The robot will be designed to move up an I-beam, carrying below it the largest load possible, while achieving that task in a minimum amount of time. You are going to use a design process that brings together everything that you've learned this quarter. You're going to blend intuition, concept generation, back-of-the-envelope analysis, computational analysis, models of motors, gears, and other machine elements, design for mass efficiency, empirical testing, technical writing, and of course, iteration. And you're going to make this system, test it on the testing rig in Darblov, and then your grades will be based on objective performance of your system, your report, and some peer evaluations from your teammates. So our learning goals here are how to apply this design approach to a more complex problem and in a team setting, how to effectively incorporate multiple custom catalog components into an assembly. That's going to be a subject of our discussions in our topic readings and videos for the next week and a half, and more sophisticated use of our motor and gear models, and also power analysis and mass efficient component design. And we'll talk more about energy efficiency in the coming weeks as well. So before you get started here, it's a good time to take a quick look around your team. Make sure that you have your Tamiya 72001 gear motor kit. And we will provide you also with some shafts and ball bearings that you can use in your project. And the I-beam will be located in the atrium of the Darblov lab, just where our other testing setups have been. All right, so what's the actual task here? Well, you are going to design a robot to climb up an I-beam while lifting as large a payload as possible for a set distance along the I-beam in a set time. And the I-beam will be oriented something like this. So it's going to be at an angle, rising up, and it will have a cross section that looks like this. And you can get the measurements here. So your robot is going to have to climb up at least a 1.5 meter section of the I-beam. It will have to accomplish that in 3 minutes or less. And it will carry a payload. You could use, for example, a 5-gallon bucket filled with weights or something like that. The payload needs to be located below the I-beam somewhere. And as you climb up the I-beam, obviously nothing else should touch your robot. Your teammates should be helping it along. And the robot and the payload have to move together in unison. No winches here. No part of the robot can be attached to the I-beam and be stationary while the rest of the robot moves. And the payload can't move separately from the robot. The one source of power, mechanical power, for your robot will be the motor that we provided you. And you'll have several of these among your teammates. You can only use one per robot. And similarly, you can only use the equivalent of one kit's worth of gears. So no more stages of gears than you find in that one kit. Fortunately, you'll have some spares if things go wrong. We've got some specifications in here also for the ball bearings that we're going to provide you. They have a radial load, a maximum radial load of about 500 newtons. Now you can use some other materials to make your robots. Of course, you're going to 3D print parts, custom components. You could use some other materials in some places like rubber bands and super glue and things like that. But the primary structure of your robot should not be, it should be composed of these custom components that you 3D print. If you have something break or get damaged, or there's an emergency, hot gluing some popsicle sticks on to fix something, okay, this is acceptable, but that should not be the primary way of making your robot. We're looking for carefully designed, precisely fabricated systems here, like those that we've been talking about this quarter. So you'll be using these Tamiya gears. We've characterized their strength for you in separate tests and provide that information here. If you want to design some custom gears for your robot, we've given you some tools to do that, and you can read about how you can use those. Here you can 3D print your own gears. We've also provided a few design tips for this scenario that help overcome some common but not particularly intellectually interesting problems that you might run into. We've assigned you teams, and we have assigned diverse teams primarily by sending you in diverse coaching sessions. And at the beginning of the quarter, we actually ran a massive optimization to try to maximize diversity in your degree programs, your strength in the prerequisite courses, and your experience in these advanced courses and with individual design of robot-like systems. And along with trying to maximize the overlap with people you want to be teamed with and with your schedule. Now, your team must work together, and we have some suggestions here for how to do that well. I recommend reading. This is a good opportunity to develop your teamwork skills in engineering problems. And at the very beginning of the project here on Monday, you should have a kickoff meeting. And in that meeting, it's essential to hold that right away so you can get started on the project immediately. And here's a few things that you need to accomplish. One is come up with goals for your team. So we have a diverse set of interests across the class. Is your team going to try to carry the maximum payload or just do enough to pass? Either are okay, but you'll need to agree on one goal as a team. And this will probably require some compromise. And you also want to divide up roles in the team, which aspects of the project will each of you lead. A good way to divide this is, say, this person's going to lead powertrain, this person's going to lead motor, this person's going to chassis, this person will lead these custom components of, I don't know, wheels, connection to the payload. Do not divide things up as this person does the design, this person does the making, this person does the reporting, which doesn't work at all. It results in an incoherent design and report. Another thing to do during your kickoff meeting is set up meeting times. You should have at least 2 and ideally 3 1-hour weekly meetings for each of the 3 weeks that we have this project. It's not that many meetings, 6 to 9 in-person meetings, and those are essential for keeping the team on the same page and discussing things effectively. Also decide on a way that you'd like to communicate that reflects your team's unique approach. Maybe it's Slack or Discord, maybe walkie-talkie, who knows. And also come up with a team name. And clever names are always appreciated. And, yeah, have fun. Now, the way that we'll evaluate your robot is that we'll have you take your robot to the I-beam and apply the payload, turn it on, take a video, and time this as it climbs up the I-beam. And we're going to give you a part of your grade is going to be based on nominal performance, and a part will be based on its objective payload performance. So the nominal performance here is going to work a little bit differently from our other projects. There will be different levels of performance. So you'll get a quarter credit for just having a complete robot, like kind of, looks like a thing that could do the task. You'll get 50% credit for a complete robot that can attach to the I-beam in time with at least a 1 kilogram payload. You get 3/4 credit, nominal credit, for a robot that can climb just a little bit, at least 0.1 meters, 10 centimeters, with at least a 1 kilogram payload, and full nominal credit for a robot that completes the full climb, 1.5 meters, with at least 1 kilogram payload. And note that one of the requirements here is that your robot needs to be connected to the I-beam in less than 1 minute. So it can't be something where you take the pieces and start putting it together, and 30 minutes later, you finally got all the little tiny screws threaded in or something like that. It needs to be fast to put it on and take it off the I-beam. And part of the reason for that is so that we can use that test setup effectively across teams. And that's necessary to receive nominal credit. The other part of the performance grade will be based on the payload you're able to lift relative to small and large payloads. And that'll work really similarly to the way we've done this in other projects in the FUS. And we're going to give out some awards. They include largest payload, manufacturing excellence for the best built robot, best style, and you can interpret that any way you like, and the best report. So what is that report going to comprise? Well, first you'll have a photo page that'll include your names and some photographs of the robot where you can clearly see all of the key features. Then you'll have a summary page in which you provide a description and reasoning. And here again, as always, we're looking for very clear, convincing, concise explanations of what the robot is and why that was a good choice given this project. And the scope of the project is pretty big, so you're going to have to be thoughtful about what matters and selective in only picking the most important things, and sophisticated in the way that you tie your choices back to mechanical systems concepts. Then we'll have a transmission page in which you'll explain how you chose the total ratio from motor speed to robot translational speed, and how you chose your applied voltage. And it's often helpful in this case to refer to some equations, maybe figures, maybe some generated using code, and you can include those if you like. You're not required to. And also on that page, we'd like to see an accounting of the power flow. Where did each joule that flowed out of the power supply end up? And so some sort of diagram showing this, along with a little bit of math explaining how you estimated each value. And then we'd like to have component pages. So for each teammate, you're going to pick one of the most critical custom design components, and then give us one page on that component. And you'll start with listing your name. So each person on the team is going to be responsible for one of these pages, and an image of the component, a short description and reasoning explaining why the component looks the way it does, and back of the envelope analysis, and finite element analysis that's relevant for that component. Finally, we'll have everybody complete a self and peer evaluation. And in this, you will explain what you did in the project and evaluate your collaboration practices. And in both of those cases, you'll talk about where there's room for improvement and what your strengths were. And then you'll do the same thing for each of your teammates. And a portion of your grade will be based on both the quality of your feedback to your teammates and their assessment of your contributions to the project. The overall project grade will be 30% based on objective performance of your robot, 60% on your report, and 10% on your peer evaluations. So this is a really challenging, exciting project. You have all the tools that you need to be successful. I encourage you to really go for it and have fun in this last project in mechanical systems design.